Okay, today we're going to be talking about how to determine whether a function is differentiable, or in other words, can you find the derivative, or in other words, can you determine the slope of the function at a specific point? And there are four instances where this derivative does not exist. And the first is when you have a sharp corner of some kind. And the idea is that the slope from this direction is, say, -1. The slope from this direction is 1. So how are you able to determine what the slope is at this specific point? You can't. It's not determined. So any sharp corner, the derivative will not exist. Any cusp, which is similar to a corner, the derivative is not going to exist for the same reason, all right, because the slopes are not approaching the same value from both sides. Clearly, the slope here is approaching a negative value, and the slopes here are approaching a positive value, so that's not going to work. The next thing is a vertical tangent. We learned in Algebra 1 that the slope of any vertical line is infinity, just like the slope of any horizontal line is 0. So that's not going to exist. Plus, a tangent is only supposed to touch the curve at one point, and if it has a vertical tangent, it's going to touch at an infinite number of points. So that's not going to work. And then the last example is if there's any type of discontinuity, whether it's going to be a vertical asymptote or a jump or a hole, the derivative will not exist. Which leads us to a theorem which basically says that if the function is differentiable at a certain point, then by definition it must also be continuous at that point, because you can't take the derivative of something that is not continuous. Makes sense. So that is a theorem that we want to keep in mind. Differentiability implies continuity. Okay, find all points in the domain of the absolute value of x minus 2 plus 3 where f is not differentiable. So first thing we want to do is we want to sketch a graph of this function. And we recognize that this is an absolute value function shifted to the right 2 and up 3. So let's just put a point right. Let's just say we have right 2 and up 3. Let's put the vertex right there. And let's just see here, we have a regular absolute value function. So here is our sharp corner right here, and that would be the place where it is not differentiable. So you'll say it's not differentiable at the ordered pair 2, 3. Okay, we want to prove that this function x plus 2 to the 2/3 is not differentiable at c equals -2. Using the alternate definition of the derivative. Now, if you graph this on your calculator, you'll see that there is a cusp at -2. But we want to prove that algebraically. So we're going to use the limit as x approaches -2. We're using the alternate definition of f of x minus f of -2 over x minus -2, or x plus 2. So f of x is x plus 2 to the 2/3. Minus f of -2. When we plug -2 in here, we get 0. So we'll just put that there. Divided by x plus 2. I'm going to put x plus 2 to the first power here. And that way we can see that essentially what we have is x plus 2 to the 2/3 over x plus 2 to the first. And we know that we have the same base and we're dividing. We subtract the exponents. So that's going to be 2/3 minus 1 is going to be x plus 2 to the -1/3. Since it's a negative exponent, I'm going to move it to the bottom and write it as a positive exponent. And notice what happens here whenever you try to substitute -2 into your limit, you get 0. And 1 over 0 is undefined. It does not exist. So that lets you know that the derivative at this point does not exist. It's not differentiable. Okay, example 3. We are given the limit as x approaches 5 if f of x minus f of 5 over x minus 5 equals 3. Which of the following must be true, might be true, or can never be true? Okay, so we recognize this to be the alternate form of a derivative. So the alternate form of a derivative basically we see here that that's just going to mean that f prime of 5 equals 3. The slope of this some unknown function at the point x equals 5 is going to be a slope of 3. So here we'll say this must be true. Now, if this must be true, then this can never be true because a point cannot have two slopes at the same point. All right, it can't definitely have a slope of 3 and definitely have a slope of 0 at that point. So that's never true. Now, this is saying that when x is 5, y is 3. Well, it might be true. Don't know for sure because we don't have enough information to know what the graph is doing and what the y value is when x is 5. We don't know. Now, f is continuous at x equals 0. Once again, it might be true because we don't have any information about this graph when x is 0. It may be true, it may not be true. It doesn't have to be continuous at x equals 0. Oh, but it must be continuous at x equals 5 because it is differentiable at 5. So therefore, it must automatically be continuous at that point as well. Now, what is letter F saying? The limit as x approaches 5 of f of x is equal to f of 5. So this is basically saying that as x approaches 5 from both sides of a function, that's actually equal to the function's value at that point. So what does that tell you about the function? It's another fancy way of saying that this function is continuous. So it must be true. So essentially E and F are basically saying the same thing. Okay, find all values of x for which this function is not differentiable. And we said that there are 4 times when a function is not differentiable at certain points. When there's a corner, normally happens with absolute value functions. When there's a cusp, a lot of times that happens with fractional exponents, like 1/3, 2/3, 1/2, that sort of thing. And then vertical tangent, and then some sort of discontinuity. So let's see if we can factor the denominator here. We factor the denominator into x minus 5 and x plus 1. So we know that x cannot equal 5 and x cannot equal -1. The function will have vertical asymptotes at those 2 points. And so if there are vertical asymptotes at that point, that means it's not continuous at that point. And if it's not continuous at those points, then it is not differentiable at these points. Okay, example 5 is a tricky problem. Let f be a function which satisfies f of 2 plus h minus f of 2 is equal to this function here. For all real numbers h, find f prime of 2. Okay, now notice here that this part right here that I'm going to underline, it looks somewhat like the form of a derivative, the standard definition of a derivative. It's missing some parts, but it looks like something we've seen before. So the question becomes now, is there a way for us to manipulate this equation so that we can make it look like this? Let me write this down. Limit as h approaches 0, f of x plus h minus f of x over h. And we know that that is equal to our derivative f of x. Well, let's just see what we have here. We have f of 2 plus h minus f of 2. And let's see if we can factor out an h here. Okay, let's see. We factor out an h. We get 5 minus 3h plus 9h squared. How about, okay, we need an h on the bottom. So why don't we divide both sides by h? Divide by h. H, not 2, divide by h, and these are going to cancel out, so those are gone. And then we have essentially we have f of 2 plus h minus f of 2 over h equals 5 minus 3h plus 9h squared. Okay, we're missing the limit as h approaches 0, so why don't we just take the limit of both sides? We are allowed to do that because in math, when you have an equation, you're able to take the whatever you do to one side, you have to do to the other side. So this whole side right here that I'm going to box in, this whole side right here, according to this definition, is equal to f prime. It's actually equal to f prime of 2. Here, we're going to evaluate this side by plugging 0 into our h's, and we end up getting 5. So we can conclude that f prime of 2 is equal to 5.